Okay, so this is Calvin Oakes. He went to his class 3 years ago? Or 2?
2? Yes.
A few cycles ago.
Yeah, a few cycles ago.
A few. All right, and so I'll let Calvin talk about what happened. But so just a few years ago, he was in the very same boat that you're in, and was working on a project and couldn't find a sensor to do what he wanted to do. And so Calvin went after it and created his own sensor, and he's going to talk about that. But so talked about thinking out of the box, right? Looking for uncommon solutions to common problems. All right, that's really what this is about, is challenging yourself, challenging your teammates, and looking for ways to do things that maybe you wouldn't normally do, right? And so I've had Calvin give this presentation, I think, 2 or 3 times now. What's that?
3rd or 4th time?
Yeah. So Calvin does a good job about talking about this and explaining the process that he went through. And so I thought that this is an excellent opportunity for you to gain a different perspective. And so without further ado, Calvin Oakes. Big round of applause. Woo! You're a rock star now.
So I'm going to go and pass this around. This is just a little display box that I did, just so you can get, look at it while I'm talking about it, and just so you have an idea. So, like Dr. Belcher said, I ran into a problem. So my freshman year when I took the class, I was like, we're like, all right, choose something you want to sort. I'm like, well, what the heck do I want to sort? And me and my group, so my 2 other partners, we're just brainstorming different ideas. And we're like, we don't really want to do something simple. We could do M&Ms and just sort by color and just.
He just threw you guys under the bus.
Yeah, he did.
What?
You can change that.
Doing that is good. But we were like, what would be cool? And we're sitting there and we're like, you know what would be cool? If we sorted dice. And boy, did we have no idea what we're getting ourselves into. So we started coming up with designs and stuff, and we had a couple ideas of how to sort the dice. So these dice that in our final project, they are sorted by the face, the number of the face. We thought about maybe doing colored dice, or maybe doing, you just do a light sensor that just says how much white and how much black. But the accuracy of one of those is just terrible. It was hard to find something that could do what I needed to. So we actually, we started working on this, and we're like, okay, we've got to find a way to do this. So I started coming up with this solution that allowed us to not only read the face of the dice, but have an accuracy of close to 98%, which for a sensor reading the number of a dice that's this large, I mean, that's a really good accuracy. So as you saw from the box, if you haven't seen already, these are the 2 sensors. So this is my first version here, and then my second version. So basically what it does is it uses infrared light that will reflect, it will emit light, reflect off of the face of the dice at a very specific location, and then reflect it back to a detector. Now this infrared light would emit, it would reflect more light if it was white, and would reflect less light if it was black. So when I was measuring these locations, I was able to know whether the very specific location was a black dot or a white space using that. So this version right here, this is my very first prototype. I mean, the back of it is ugly as crap. I mean, I just sat there and I soldered for 6 hours just to see if it would work. See if the concept was even obtainable. And well, once we got that, we're like, oh my gosh, this is working. And it's actually telling us the face of the dice. It did take like a lot of programming stuff, but like I eventually got to a place where I'm like, this concept will work. So then, with some of Dr. McClurg's help, we worked through and I designed a board here that makes it a lot cleaner. And then also, if you see this chip here, so that chip's not on here. So we actually added a feature in the final version that essentially allows me to control each individual location, and I can turn it on, check it, turn it off, and then check the next one. That way I've got a lot less interference from the other emitters so that I would get a very accurate result. So then I also designed these just pin headers that make it really easy to hook it up to the Arduino that I had. Because I wanted it to be essentially plug and play. Like you run the library, you plug it in, and you call it a day. So that's the final version that I've got there. But I would not have gotten there if it wasn't for my first version. That's the idea of like prototyping. So like you just kind of throw something out there and you're like, well, does this work? I don't know, let's try it. Like, it's okay to just go out and fail and make mistakes. Like, if you have this idea and you want to go out and you just try for it, you know what? If that fails miserably, you know it didn't work in the first place. So you just go and you just try it, and so that's what I did. I spent 6 hours soldering a board that I had no idea would even work, but when it did work, I realized that this is a good concept, so I made it into a more final version. So now if you notice, so here's my schematic here. You guys will learn about schematics in this class.
Yep, not yet though.
So this is a schematic and then a board layout. So this is designed in a software called Eagle, which is a electrical CAD software that you guys will learn in this class, and then you'll get even more if you take circuits. So these are the schematic, and then my board layout there. So this is just taking time to lay out all the parts, and then once I had a board layout, we actually milled it upstairs, and which gave it a more professional look to it. So if you have noticed, there are only 5. You're like, well, why wouldn't you do all 9? Well, so there's actually, with dice, there's a lot of symmetry involved. So you actually don't need to measure all 9 locations to know the distinct difference between the 2 different dice numbers. Because there are only 6 numbers. Now if I was doing like a 25-sided dice, that'd be chaotic, but like in this case, I only needed 5 locations to know exactly what number the dice was currently. So, so as you can see here, you got your standard layout, and then it's kind of hard to see, but so these are grayed out here because I don't need to read them. Because as you can see here, these 5, that's distinct, that's distinct, that's distinct, that's distinct. So all of those are all different distinct values. And that's the same if it's rotated 90 degrees. Because you had to account for the rotated 90 degrees and the normal. So then my diagram over on the side, those are the values that, so I had to do fine tuning when I did this. So I had to put a dice over and I said, okay, well I know exactly what I've just laid down. What numbers am I getting? So what I did is if the number was greater than like 225, if the number I was getting is greater than 225, I knew that that space was white. If it was black, it was less than that. So I did that, and each infrared light is all tuned so that I know exactly what number I should decide says whether it's white or black. Now, it's normally far from that number on both sides, so it's not like within a 2. but I also didn't want to. I wanted to have a good center to make sure that any variance there was, I was able to deal with. So this is our final project. So the bottom base would spin, and it would rotate to the correct location, and that was a whole problem of itself that I'm not gonna get into. But so inside this black box here, we would feed it into the top. It would slide down, and there was this. It was a like a what a water mill would do, where it's like it has like spokes, almost like a spoked wheel, and it was the right size to where it would catch the dice, hold it exactly in the position of the infrared dice sensor, and then spit it back out down the chute. So that took a lot of like tuning and getting that right. So that took a lot of iterations too. But we did eventually get it, and so you could feed it, it would measure, and then it'd spin the base, and it'd spit it out exactly on the number that it was. So we were very, when it first worked, we're like over here like, oh my gosh, it's working. And that moment where you're like, this is pretty amazing, and you feel accomplished of your work. Like that's what all of like the struggling and figuring out is for. Like getting to that point where you're like, oh my gosh, I did this. So like, and this is freshman me. Like this presentation isn't here to be like scare you into like, if it isn't like this, you're not qualified. Like it's just like, I was a freshman, and I just kind of sat down and tried to figure stuff out. I tried things. I was like, oh, this could work, this could not work, I don't know. And I just sat and I just tried it. And if I failed miserably, I would have known that solution wouldn't have worked. So just, when you're in this class, like, go try things. Like, go, if you have this grand idea, just try it. Like, don't let failure or it falling apart decide whether you should try it or not, because you don't know if it'll work until you've tried it. So, does anyone have any questions?
So one comment on that, on the grading, notice the actual final design, the working final design is worth 5% of your final grade. So we really care about the process. We would love for you to get a working design, but if you try something and disaster strikes, and you've done everything you can to try to make it work, you've gotten help, you've approached the problem in the right way, and at the end, you drop your design or sit on it or something, and it's toast. Absolute worst case is a 5% hit. So feel free to try things. That being said, this team definitely was very active in seeking out help. So they ran into a lot of problems. And, they also got a lot of help to solve them.
Yes. Yeah, Dr. Doucher helped us a lot with some of like the mechanical aspects, because there's this gearing system inside here that you can't see. That was a pain in the butt. And so Dr. Doucher helped us figuring out the gearing and like how we should go about that. And we were having torque problems, like I wouldn't even spin the base because it was too heavy. So like he helped us a lot with that, and Dr. McClurg helped with all like some of our electrical problems we had, so some of the problems with the sensor and figuring that out. And I didn't have Dr. Zhao, but Dr. Zhao is great at it too. And so like just go ask them too. Like you don't have, it's the whole point of this class is to learn and figure things out. So you don't have to feel like you have to do everything. So
You guys aren't flying solo, right? You've got your team members, and you're going to come to us and ask us questions. We're not going to give you the answer, all right? And Calvin will tell you that he went through 3 or 4 different iterations to get that thing working. And I never gave the answer, but I asked questions.
Yes.
Right? And I asked very thoughtful questions
Mhm.
about, have you thought about this, and why do you think this is doing that? And so this is about learning, and it's about growth. We're not gonna give you the answers, but we're gonna steer you in the right direction.
Max, do you have
Yes, Max.
How quickly could it sort a dice?
Slow. The motor we used the, have they gotten their kits yet?
Yeah.
Oh.
Yeah.
So in your kit, there's a stepper motor, and we had a lot of coding problems with that too. So we were not able to run it super quickly. I mean, we're talking like, I think you guys have like a standard now, isn't it? Like,
It's, the standard is defined according to the application.
Yeah.
So,
well, ours was slow. I mean, we're talking like 20 seconds a dice. Like, I mean, and that wasn't because of the sensor's problem. The sensor, once it got in there, it read it immediately. But the base just kind of sat there, and you just watch it, and you're like, come on. So if we had more time, I think we would have tried to get gearing to make that spin a lot faster without the stepper motor having to spin as much. But yeah, it worked. So
right, good. Well, let's thank Kelvin, and I have a couple of things to mention before we head off to our groups. Is every day meet as a team at some point. This can be even during the lab period, if you don't have any other time when you're all together. And get everybody on the same page with what has every individual in the team done. Also get everybody on the same page with what are the current things that are stopping you from moving forward. And then get everybody on the same page with not just what's left to do, but who is assigned to do what. And those three things are pretty simple, they're pretty standard for any sort of task management process. We're not going to teach you all of the details. You can go down a really big rabbit hole in managing the process. This isn't a process management class, this is a intro to engineering class. But having you walk through this exercise as a team every day will really help you make progress. So when you're done with that, have everybody log into Moodle and click on the daily progress form. Since I'm not eligible to take the questionnaire, I guess I'm not a student.
Maybe you can switch
change
to
your
the
role.
students even more.
Oh, good idea. Switch role to student. Aha! Then I can answer and just type in a summary of what you did, what's stopping you, and what you have to do. And this to-do list, the team leaders have a little different responsibility. So you as an individual, if you're not the leader, just write the things that you are responsible to do in that. As a team leader, you need to know what everybody needs to do. So you'll want to keep track of the whole to-do list in that box. Okay, and just do that every day, and that will start. We'll start checking that tomorrow. So go ahead and have your first meeting today or tonight. And then every day in the future, fill out that form. Okay? So 2 things, fill out the safety survey. Thing number 2, make sure to have a daily meeting. Yeah?
Does that include weekends?
Oh, every school day.
Or school day?
So not including the holiday and not including weekends. Good? All right, so the other thing that we're going to do is we're going to have everybody go to the appropriate spot. So upstairs, all the team be. Basically, if you were upstairs last time, go downstairs. If you were downstairs last time, go upstairs. And we'll kind of get you started. And then all of us professors are going to meet for 20 minutes or something while you guys work. But we'll get you started.
Record, you get the little red button.
5 and at 1 o'clock, before we come up here, I'm gonna look in the lab room, and if it's clean, then everybody's good. If it's not clean, then I have to start trying to hunt down whose fault it is and start taking away points, and I don't wanna do that. So just, when you pick a tool, use it and then put it back. When you're done working, put all your stuff back in your bin, and everything will be happy. Policy on personal devices. The idea is we have computers available for you, enough for everybody, especially when you're connecting a circuit like an Arduino or some other sort of measurement. When you're connecting something to a computer, there's always the possibility of that thing damaging the computer. So I would much rather have our lab computers be damaged, and we have budget to replace those, than have your laptop be damaged, because I'm not gonna pay for that. Similarly with, I mean, I would like to, but it's just not possible. Similarly with the charging, we have these really weird power strips on the ceiling. And occasionally people like to charge their phone up there. I very strongly recommend against it, because they fall off and can get cracked and break, and just not a great idea. So if you use your personal equipment like laptops, phones, etc. in this room, it's completely at your own risk. So just be aware of that risk. The next thing is soldering safety. So we'll get into more details on soldering safety later when we actually do soldering. But just in case you get really gung-ho and want to do some soldering before we teach you how to do it, the most important thing is wear eye protection, because when you heat up the soldering iron and you heat up some solder, that solder can splatter and could go in your eyes. So A, don't stick your eyes right next to it, and B, wear eye protection. If you do end up getting something in your eye, we have an eye wash station immediately across the hall. So this room 228, the senior lab, that has the eye wash station. So it's right on the side. A quick story, I was being dumb when I was an undergraduate, and I thought it would be a great idea to solder on a wire on both ends of a battery, which I didn't think about the fact that there is liquid inside a battery, and you're heating up an enclosed metal canister with liquid inside, which is exactly a bomb. So explode in my eye. I was in a chemistry building, and you would think there would be eye wash stations all over, but at least in that building, all of them were behind locked doors. So I was like running around with acid in my eye. I finally found somebody to let me in, and I saved my eye, but don't mess around with your eyes. You can't really replace them very easily. So fire extinguisher, there's a fire extinguisher there. Don't start any fires. The biggest risk of starting a fire is leaving your soldering iron not in its holder. They remain hot for quite some time even after you turn them off, so just be careful. Electric polarity, voltage rating, and electrostatic safety. The idea with this is, given the voltages and currents that we're working with, it's more likely that you're going to damage the circuit than that the circuit is going to damage you. So the most common thing that's probably going to happen is, because it's winter, we will build up a static charge. One of you, all of you, will build up a static charge on you and then touch an electronic device and break it, just because you touched it, just because you have static on you. The way to avoid that is, always before you touch any electronic device, touch some larger piece of metal, like this this metal on the side here, or touch the metal up on the ceiling, or you can touch the metal desk down below before handling electronic equipment. The other thing is pay attention to power ratings. Different equipment takes different power requirements. So a 12-volt thing cannot be powered by a 24-volt power supply and live. So know what you're plugging in before you plug it in. If you're not sure, always ask. There's a little sign up there that says, choose wisely which power supply you use. And I think that's that. I already mentioned the soldering stuff. So, but there's other additional detail in the lab prompt. Okay, so from there, we're going to go to talking about brainstorming. Now, I'm going to introduce this, but there's lots of additional detail in the lab prompt under this brainstorming session. Now, I'll talk about what I mean by the different things, but this is to guide your discussion. Now, you've already done some brainstorming previously, so you can basically take what you did yesterday and get it into a nice format like Dr. Delcher discussed today that has clear requirements, clear scope, clear specifications, and you probably also already worked on implementation ideas, but maybe you can add some ideas. Who knows? But let's quickly introduce this thing number one, scope. The idea with scope is big picture. Who is using device? What is application? So Dr. Delcher defined a scope as you take an unsorted set of things and you end up with a sorted set of things. That is a little bit more general than I'm looking for. I'm looking for, an example would be, one of the teams is doing a screw sorter. So they're thinking, when you're at home and you have your home workshop, you open up a drawer of screws and there are all these random screws, they would like to sort them. So who are you designing this for? Well, you're designing it for a homeowner who has random screws lying in a drawer. And what's the end application? Well, it's to take that random set of screws and sort them for use in home projects. So figuring out who you're designing for is helpful. The other thing is, this needs to be something that's interesting to you as a team. That's one of the things that we care about. You're not just designing for us, you're designing for you. So if it's something that you feel is totally pointless, that's not a desired outcome. It can even be something that's silly and goofy, if that's something that everybody can get behind. But just be able to get behind it. So need to have team buy-in. So thing number two is requirements. Ooh, my Rex. The idea with requirements are, we gave you these three very vague requirements. Those very vague requirements are must sort to criteria, it must sort fast enough, and must be accurate enough. Based on your scope, you need to define how fast is fast enough. You need to define how accurate is accurate enough. You also need to define, is 2 criteria really enough? So if you give me your application as I'm sorting change for a vending machine, and you say I'm only going to sort by 2 different sizes, then I know 2 coins that are about the same size. So that requirement may not be appropriate for. So you may need to rethink your scope. If you don't think you can meet this requirement, maybe rethink your scope. Vice versa. The other thing is these fast enough write units. So, and also accurate enough write units. Those units need to be appropriate for the application. So if I said 3 screws per second, that's not something that the end customer can easily wrap their head around. But if you were to say a handful of screws, parentheses, approximately 30 per 5 minutes, then that's something I can easily wrap my head around as a end user of this screw sorting device. So that's requirements, think about those. And then specs. Boy, this marker, it's a disaster. 3 specs. The specs are measurable aspects of the design. So it's similar to a requirement, but said in a measurable way. So these need to come with a measurement idea. So sorting 2 criteria, that's fairly straightforward to measure. By the way, each requirement should have an associated specification. So the requirement is must sort 2 criteria. Maybe the spec is able to sort by able to distinguish standard coins from each other. Similarly, fast enough needs to be specified in a measurable way. So you can say, I plan to measure the speed with a stopwatch, or I plan to measure the speed in this other way. Similarly, accuracy, etc. How I'm going to run 10 runs of 100 coins or something like that. So these, oh, thank you. These need to be measurable. Basically, think of them as so maybe you find out that you're able, when you actually go and do the testing, you find you way exceed your requirements. So you're not able to write the full spec yet because you haven't done the measurements and you don't know what your specification is. But you can at least write the test that you're going to do to try to measure the speed. And then later on when you're finally done, you can write a specification that says, I'm able to sort this fast, and I can guarantee that. And that's above my requirements. So these are the measurable outcomes. You don't know yet what the actual outcome is, but you can at least write the test. So a sample test. And this can be like a 1 sentence. Then for implementation ideas, the idea is you need a sketch. And you need more than one idea. Now you don't end up having to try all these ideas. Maybe you try your first idea and it works great, but you need to at least have more than one idea in the pipeline. So always have a plan B in your back pocket. Okay, so questions on this brainstorming, like what the goals are. I'd like you to generate, I'll say here, so sentence for this number 1, This one is a list. List of 3 recs for number 2. This one is list of tests. And this one is just at least 2 sketches. So maybe you already have this one, but you can at least work on these guys. Okay, questions? Yes?
By sketches, do you mean, is that like one part of it we're looking at, or like the whole thing?
Whole thing demonstrating the major operating principles.
Okay.
So, yep. And by 2 different ideas, maybe most of it looks similar, but you're going to try the arm in 2 different ways, something like that. Okay? All right, so we're going to leave you for approximately 20 minutes, Dr. Zhao and I, and go discuss with, oh wait, did Dr. Delcher say 2:30? He said 2:30? Did he say that we were meeting him at 2:30, or are we meeting him like right now? Yeah, give me a second to run downstairs, and you can continue brainstorming. I mean, you've got like 30 minutes or so of work to do anyway.
That's just kind of
Thank you.
Well, this is Arduino kit we ordered for you, so you can keep it.
I see. So is that like,
Work with who use it, who builds.
so we got the fun one,
Stuff
stuff like that.
And now just take a look. So we will talk about it.
So yeah. And the funnels are here, right? And it's funnel them, all we're gonna do is the skills go out, and the skills will go straight through. And the image will hit the slides, like you do a little bit of scroll.
So does it just need like a little wall sticking out of those where it'll hit it and it'll just go?
And because it's, the gap is too small for them then, those hit this. It's funnel and it rolls in like a ramp onto like, these two are here. And so, right here is gonna be a smaller, like, together, and then as it goes, it gradually gets bigger. See what I'm saying?
Or
For like the scale or the M&M or something, so like, once it gets,
Oh, so
That's
once it
true.
gets too big, then it drops
then
down.
it drops down, and then at some point, since it's big enough, it soon will drop here, and then we could do one of those.
Which is basically the same idea. but-
Same idea, but 2 different types of.
I kind of like having fun
Like-
with this.
It gets bigger and it's still
Yeah, that's, we could do it like that,
It's
or we
basically
could do,
the easier way of doing the whole thing.
or we could,
We'll try both anyway.
we could do it like this, which I
Johnny,
think
do you know how to stop this
is
thing?
faster, to get honest.
We can do that one and that one, and see which one's better.
Help you discover your what things you still have to do. And that's actually a pretty hard problem. Like, how do you know what you don't know? And the way you can discover that is by asking yourself questions of like, who's going to end up using it? What do they really want? In more detail, once you think you know what they want, try to think of a test that you can test that. And if you can't think of a test, maybe you need to rework the requirements. Then once you have sort of testable requirements in place, then start thinking of actual ideas. And this way your actual ideas will be good ideas. So that process helps you discover what you don't know and helps you generate better ideas. This process helps you understand the technical details of your implementation ideas in more detail. For example, let's say in step 4 above you come up with this sketch. Like, you think you want to sort by color and temperature or something. Seems like a bad idea because then you have to maintain like a cooled, like a chilled reservoir and an unchilled reservoir, but let's say that you want to sort by color and temperature. Once you draw this sketch out, you have an idea in your mind of how it works. The idea of a system diagram is nothing more complicated than just trying to identify the different pieces and the interfaces between the pieces. So what each part of the design does, each part of the design is going to have some thing that's coming into that part, and it's going to, basically it's going to have something that it requires to work and something that it provides. So the thing that this piece of the design here, this piece, I'm going to call this the hopper subsystem. And you can give each piece a name. The thing that it requires are widgets. Let's say that you're sorting hot and cold widgets. And I'm going to say mixed. Now, what comes out is just a single widget. And kind of be specific, because this guide doesn't provide a sorted widget, it provides an unsorted widget. But it gives you just one of them, so that you can deal with one at a time. That guide goes on to the conveyor subsystem. And basically just ask yourself, what is the point of this thing that I drew? And that way you can think of a name for it. So the point of the conveyor is to take a single unsorted widget and move it to a certain spot. So the outputs of this conveyor are widget at a certain spot. Like a physical location. Those are different locations, and see how I didn't really go into a lot of detail? That's totally fine. What you're trying to do is communicate the point of this subsystem with a word or two, and then also the thing that this subsystem requires and the thing that it provides. So the only thing that I'm requiring of this guy to provide is to just move the widget along. This guy sends it to either the color sensor first, and so you can just call this guy color. The thing that it takes is the widget needs to be in front of it, so that's good. Something that I forgot is that the color sensor actually needs a light to shine. So that will help you identify things that you forgot in your drawing. So light. Because in order for the color sensor to work, you have to have light reflected off of the object. So the light needs to shine on the object in order for the color sensor to provide information. So what the color sensor provides is a color. And actually, this gives me an idea that this diagram is slightly incorrect. Because in order for us to get to the temperature sensor, this conveyor needs to know the fact that the color sensor is done. So the color sensor should also give like a done signal here. And this guy probably doesn't even actually need to know about the color yet. Okay, so incoming to this guy is a widget. So I guess I'll draw this line here. And you can see my diagram is getting pretty messy. That's okay. Just make your messy diagram and then clean it up when you're all done. So incoming is a temperature sensor. The widget comes in and gets sensed. Now, the temperature information does need to go back to the conveyor to tell it to move again. And also the color information needs to go back to the conveyor to tell it, which spot to move. And I also need to get a done signal back here to know that I'm done. Once all that is in place, now the conveyor can send the widget to one of the ends, and it's going to go into the hopper sorter, or the bin. I'm going to call this a binning system. This doesn't just get the widget, it also needs to know the temperature and the color too. So incoming is temp and color. So it knows which way to run the switches. And then output here is the sorted widgets. And then these are just the bins that it sits in. So that's the idea with the system diagram. It's really just a systematic way of describing the behavior of your implementation idea. And I don't want you to get into too much detail. I almost went into too much detail here. I would like, especially since this guy might change, but I do want you to, as a team, get practice in translating, like basically I want you to get practice in figuring out what are the subsystems and think about what their inputs and outputs are. And if you've done that, then you'll be good. So questions on system diagram. The blocks are named with the subsystem name. The arrows coming in are the things that those blocks require. The arrows coming out are the things that those blocks provide. And the different subsystems are connected with each other with arrows, showing all of the different interactions between the subsystems. Okay? It'll probably take a little bit of sort of scratching your brain, because you've probably not done this kind of diagram before. But give it a shot, and we'll be around to help. The next thing,
This and everything.
which is oh, actually, yeah, I'll go ahead and introduce the Arduino kit. So everybody hopefully has already looked at their Arduino kit, but if not, I just want to walk through a couple of the things that are in there. And Dr. Zhao did this last time, so you'll have to be gracious with me if I stumble a bit. The link that's provided in the report, that gives you a list of all of the stuff that you have. If you look under tech specs, that'll be a list of all the things. And then if you click on this, it'll give you more information about those things. Some of the things to point out. potentiometer. This is a sensor that allows you to detect an angle. So you twist this knob, and there's a way that you can hook it up that lets you detect what angle you twisted it to. A tilt sensor. This tilt sensor does not allow you to detect an angle. It allows you to detect whether it is tilted or not. So it's a threshold. Like, have you tilted it on its side, or have you had it straight up? The phototransistor allows you to detect a light, like the amount of light that's coming in. And that's also true with a photoresistor. Some of your kits have photoresistors, others have phototransistors. Generally speaking, the photoresistors are better at detecting amount of ambient light, whereas phototransistors often come with a filter on it to detect a certain wavelength of light. So your color sensors are actually 3 separate phototransistors all integrated together to give you an amount of red, an amount of blue, an amount of green. This piezo capsule, this is a little speaker. It's like a little buzzer. So if you want to make an annoying sound, you can use the piezo capsule. LEDs, those are light-emitting diodes. I'm sure you've seen them. The trick with an LED is that they have a polarity, and they also have a maximum current. So in order to avoid burning these guys up, you always need a resistor in series with them to prevent the LED from getting burnt up when you light it. What else? Motors. There are 2 motors in your kit. One is a stepper motor. The other is a servo motor. So maybe can I borrow a couple of these? So I'm just going to quickly borrow this one. So this guy is a stepper motor. It has a high torque. It can turn, it's strong, I guess, is another way of saying it, but it's slow. You can also control the speed of it and the direction pretty easily. This is a servo motor. The purpose of a servo motor is you tell it an angle to go to, and it goes to that angle and maintains that angle. If you want it to move, you have to tell it a different angle to go to. This type of servo does not go around 360 degrees, it only goes around 180 degrees. So just be aware of that. These aren't as strong as this guy. So there's a third motor in here called a DC motor. These motors are very low torque, but they are very fast. So hence why it comes with a little fan. So this is the kind of application you need where you want something really fast and low torque. If you want this guy to turn anything with any weight to it, you're probably going to need to get a little gearbox to gear down this so it can actually turn. Okay, what else? There's also a bunch of integrated circuits that I'm not going to get into right now, but they have different helpful functions. So don't break those because you might need them. What else? There's an LCD little display. We have a slightly easier way of connecting these to your Arduino. So the one that comes in your kit has like a 14-pin interface, and we have a little adapter that we can hook on there that lets you plug it into your Arduino with a 3-pin interface. So if you plan on using one of these, it's worth talking to us so we can get you the the 3-pin interface. Yeah, so just an encouragement, play around with what's in your kit. If you're not sure what a certain thing does, just ask us, because it might be a cool feature to add to your device. Also, please get to us quickly if you think you need anything that's not in the kit, like an extra motor, a bag of marbles, things like that. We have to buy those, so let us know quickly. Questions on Arduino kit? Yeah.
Do you have a color sensor?
We do, yes. I'll get those. I'm supposed to get those to you today. Aren't I? I'll get those after this. One other thing I was going to say is some of your parts come in a little silvery bag. That silvery bag is not just shiny because it looks cool. It protects those devices from static. So store your Arduino inside the silver bag. That will help keep it alive. Okay, so the next thing I want to do is talk about this cloud drive. So the cloud drive is called Autodesk Desktop Connector, and all of the lab computers have it installed already. But in order to use it, you have to sign up for an Autodesk account. So the way you do that is just type Autodesk Education, and then click on this. And you have to give them the details of which school you go to, so they know you're at an educational institution. And for whatever reason, the internet doesn't work. Okay, never mind. So you just click get product, and then get started, and then type in all your details here. Once you sign in, it should look something like this. Actually, Young, do you have an account here? Because I've forgotten my password, and I think it's probably password to SD. Great, thank you. So what you can see here is a list of all the products that you have access to. So the product that we're going to be using later on in the class is Fusion 360. So if you want to go ahead and download that now, you can. You don't have to, though. The product that you need is called the Autodesk Desktop Connector. Now, if you really don't want to install anything on your computer, you don't have to in order to use this. So I'll show you the route of not installing anything, and then I'll show you the route of installing stuff. So just type in Fusion 360 Cloud Drive. And then click on this guy. Autodesk Drive. Another way to get to this same exact spot is by typing in Fusion 360 Themes. So that'll also take you both go to the same drive. So let's walk through the process here. So it looks like what you can see is all the projects that you created. You can click Create Project, and then say, like, that. Once you've created a project, then you can see who's in that project. Just click the invite button and you can invite all your team members. So now I'm a member of that team. And if you want to add files, all you have to do is just drag those files into this window here, and the files will show up like this one, for example. I can add that file. So that's the route of not having to install anything. The route of installing something, you can get this on your desktop to show up just like a regular drive, like your C drive or something, by typing in Autodesk desktop connector, and just click install desktop connector here, and you can download this. Once you download that, you're able to log in. I really need to remember my password a little better. Maybe I try one more time. I put bot into it. Right click on there. Yes, I do. Okay, so now that it's nicely signed in, you have, if you just go to the Windows Explorer, it shows up as a drive. So, like under this PC, there's this Fusion 360 drive. And you can see under this Team Dave, I made this folder called ENP104 project, and I uploaded this file. And you can just drag files into there, or open this, or edit it as you wish. Okay, if you don't, like if you make a mistake and you want to get rid of a folder, it's like removing a project is a little bit weird, so I'll just walk through this. It's not called delete, it's called archive. So like I wanted to get rid of this project, I can get rid of it by doing archive. And then if you want to delete the archive, like permanently, you want to really delete it, go ahead and look at archive projects. Let's see. Like you kind of have to dig for it to even find the archive projects. I don't remember how to find that, but if you are concerned about Autodesk stealing your data or something, let me know and I'll show you how to delete the archive project. Okay, so I'll walk around and help people get logged in. If you're on the Mac, the easiest way is to just use this Fusion Team web interface. The other way to do it via the actual Fusion 360. That also has an interface to this cloud drive. It basically shows up on the side of Fusion 360. All of your projects do. And I'll show you that in just a second when this starts up. Okay, I'll just walk around and help people. That's taking too long to start up.